All right. So this next section, if you just look at the title, it seems like it's an important title, the fundamental theorem of calculus. Okay, so it is a big idea. And what basically the fundamental theorem is talking about. So, at the beginning of the year when we talked about the fathers of calculus, there was Leibniz and Newton. Both of them developed this relationship independently of each other. But what the fundamental theorem of calculus does is it shows the relationship between the two things that we've studied so far in this. Okay, so in the first sections of this, what we talked about was we could find the area under a curve, all right, by using an integral. All right, so this idea that taking like rectangles and then finding the limit, we discovered, either the upper limit or the lower limit, that when you took the limit of the sum of those rectangles, we could represent that using a integral. Okay, this part right here, where these two values are the bounds. That's your A and your B, your upper bound, your upper bound and your lower bound. And then whatever this function was, that was the function of your curve here. All right? This we refer to as the definite integral. So to find the area under a curve, we can find the integral. And then we did these integrals on your calculator. We just typed them in and it gave us what the integral was. Okay, now in the second section, the stuff that we just went over on the assignment had to do with a function and finding its antiderivative. Okay, now when we talked about that, the notation that we used was if you had a function, all right, its antiderivative was represented by f, capital F. Okay, and what we found is if you took the derivative of the antiderivative, you ended up with the function. Okay, that's what this is saying. Okay, that's what was developed in this section in 18b. So for example, if we looked at, if you had a function 1/2 x, okay, then its antiderivative is 1/4 x squared. Are we okay on how to get this? Everybody knows how to get from here to the antiderivative. Are you sure? Yes or no? No. Okay. So what we just did on that assignment was if I gave you if I said, okay, here's your antiderivative, or here's your function. Okay, what function created that when you take the derivative? So what did you do to this? Plus 1 divided by 2, right? So we called that the antiderivative. Okay, this is the antiderivative. Okay, so what we found was if I take the derivative of this, so if I took the antiderivative and I said, okay guys, what's the derivative of that? What's the derivative of this? So if you did the derivative, the 2 comes out front, subtract 1 from the exponent, divided by 2, you get x. You get back to where you started. Okay, so if we go this way, that's the derivative. So if you take the derivative of the antiderivative, you get the function. If you take the derivative of the antiderivative, you get the function. Do you understand what I mean by this right here? This is the derivative of the antiderivative, you get the function. So the derivative and the antiderivative undo each other. And you're just back to what you started with the function itself. All right, so if we started with a function that said 1/2 x, okay, if this was 1/2 x, and I said, okay, what's the antiderivative of that? Well, you know it's going to be one more okay, now if I did the derivative of this, it would normally equal x. Okay, if you did the derivative, you'd get x. But now I want to get 1/2 x. So how would I make this? What would I add to this so that once I do the derivative, I get that? Okay, divide by 2, or multiply by 1/2. So the antiderivative is really x squared over 4. That's the antiderivative. Okay, now if you took the derivative of this, you'd end up with 1/2 x. Okay, so I'm going to do the derivative of the antiderivative. Okay, so the 2 comes out front, subtract 1 from the exponent, and then reduce that, and you get 1/2 x. So the derivative of the antiderivative is the function. That's what I wrote right here. The derivative of the antiderivative is the function. So when you see this notation right here, guys, this d over dx, this just means derivative. Okay, capital F is the antiderivative. So the derivative of the antiderivative is the function. Does that make sense now? Or now? We're okay? All right. So that's the relationship that we figured out in section B. Okay, now what the fundamental theorem of calculus does is it shows the relationship of these two things. Okay? So there's two parts of the fundamental theorem of calculus. Okay? The first part we refer to as the theoretical part. And what it does is it establishes the relationship between integrals and derivatives. Okay, there's a relationship between these two big parts of calculus. All right, what the fundamental theorem of calculus says is, when I see this right here, guys, what do I say? Derivative. So the derivative of, what's this called? The derivative of the integral equals the original function. So it's just like this. The derivative of the antiderivative is the function. The derivative of the integral is the function. See, it's the same idea. So it's showing a relationship between integrals and the original function. If you take the derivative of your integral, you're going to get the original function. All right, now, if you open up that applet I think it was the second one, and it looks like this. This is showing you that relationship right here, okay? So let me explain to you what you got. All right, this function right here is the function 1/2 x, or it's 1/2 t. All right, that's this line right here. This line has a slope of up 1 over 2, up 1 over 2. All right, okay, now, if I, let's put that right there. Okay, if I asked you, what's the area of that shape right there? Okay, because if you, at that point right there, it's about 1.5. Okay. All right, let's move A over a little bit. Okay, what's the area under the curve right now? 2. Okay, so as I move this to the right and left, the red dot is telling me what the area is. The y coordinate of the red dot is telling me the area. All right, okay, so let's move this back where it was, I think it was there. So let's go between 1 and 3. Okay, now over here on the right, I'm going to plot the slopes. Okay, so you notice that slope right there is 0.15. So at 3, the y coordinate is 0.15. Now if you just click on X and use the right and the left arrow keys on your computer, you'll see that when we plot the derivative of the area function, we get the original function again. That's the fundamental theorem of calculus. If you take the derivative of the integral, you get the original function. Okay? That's what that's demonstrating right there. All right, so let's go back to this. Okay, so that's the first part 1 of it. Okay, what are we done here, guys? When's the bell ring? 8 minutes? All right, let's go on. So that's this part. Okay, now, what the second part of it, we call the practical part. Okay, the practical part tells us how to evaluate a definite integral. Before, the only way you knew how to evaluate this was to plug it into your calculator. Okay, our calculator could do integrals. What this shows us is, how do you do an integral by hand? This is showing you the magic, supposedly, that occurs inside your calculator. Okay, the magic. All right. So, let's see how that's done. And then I'll show you again how to do it on your calculator and how to do it on Desmos. And then we'll show that you get the exact same thing as if you follow this theorem here. Okay? All right. So if we're going to use the fundamental theorem of calculus to find this integral. All right, so let's take this and we're going to write it as an integral. So this is going to become f of, it's going to go from 1 to 2. Our equation is x cubed dx. Okay, let me move this over a little bit. Okay, from 1 to 2 of x cubed dx. All right. Now, what this says is, to get the answer of this, you take the antiderivative. Okay, so you got to figure out what's the antiderivative of x cubed. x to the fourth divided by 4. Any questions on how to get that? All right. Then, this is just notation here. 1 to 2. Now, what you do is you plug those values into your, this is your antiderivative right here, guys. This is capital F of x. So now we take the upper bound and we plug it into that. So that would be 2 to the fourth divided by 4. Then we take the lower bound and we plug it into our antiderivative. And that would be 1 to the fourth divided by 4. And then you subtract those two. Okay, so 2 to the fourth, that's what, 16? Okay, over 4 minus 1/4. So that's equal to 15/4. And that's your integral. Okay, this is equal to the area under this curve between 1 and 2. This is the area under the curve. All right, now do that on your, open up your calculator and let's do it. You guys got your calculators handy? Okay, so to do this on your calculator, you're going to press Math, go down to 9, that's the interval, hit Enter, and now just plug in your numbers. Okay, so let's see. That should be a 1, not a 6. Okay, 1, 1, enter. What was the upper one? 2. Okay. Then your, okay, x to the third dx. Okay, enter. Pardon me? Okay, and that's the same as 15 over 4. Okay? So, before there were graphing calculators where you could just plug it in, that's how you evaluated an integral. Okay, now, you got your laptops open, just open up any Desmos file. I'll show you how to do integrals on Desmos. So just open up any Desmos calculator. Okay, type in your original function, f of x equals x cubed. There it is. Okay, now on the second line, type in the integral. So open up the calculator and under functions, let's see, there should be an integral key. Okay, INT. J-I-N-T. I don't know what's going on with my left. Okay, there we go. Okay, now you just type it in. So it was what? 1, whoops. 2, 1. Okay, this was X. You can just put f of x dx. You don't have to retype it. And there's your integral. 3.75. Now, it's not showing you the picture. It's not showing you the graph of it. This isn't set up to do that, but that's how you do integrals on Desmos. Okay? Good to go? All righty. Okay, guys, so we left off talking about how to, the second part of the fundamental theorem was how to actually evaluate a definite integral without having to use our calculator or use Riemann sums, the stuff that we had done back in section 1. Okay, so let's see, we did 1 yesterday, correct? So do you know how to check this on your calculator? Do you guys need me to go through the keystrokes? Everyone's okay with that? Okay, let's go on to, yes, no? Okay. All right, so we want to find the area under this curve from 0 to 2. So if we were to just to have a picture of what that looks like, okay, square root of x looks like that. So that's our function, and then we're finding the area under that curve between 1 and 2. So we're finding, what's this area? Okay, so we can write that as an integral from 0 to 2, square root of x dx. All right, so you now got to find the antiderivative of this. Okay, so if you had x to the 1/2, okay, we know the antiderivative is going to be 1 more than that, so that's going to be 3/2. Okay, if I took the derivative of that, I'd have 3/2 x to the 1/2, but I want it just to be 1/2. All right, so we'd have to divide by or multiply by 2/3. So this original would have to have a 2/3 in front of it. You follow? Okay, that's your antiderivative then. 2/3 x to the 3/2. And now you're plugging in your upper bound and your lower bound. And then evaluate those. Okay, so without getting into decimals in your calculator, what's 2 to the 3/2 power? No calculator. It's the square root of 2, then what? Cubed. So you're doing the square root of 2 cubed. Pardon me?
Do we not calculate like, because the square root of 8 is like 2 point in the decimals?
Right, so, but let's say we're giving the exact answer, not the decimal answer. So if you did the square, if you had 2, okay, 2 to the 3 halves, so that's the same as 2 to the 1/2 cubed, and 2 to the 1/2 is the same as the square root of 2 cubed. Okay? So that's root 2 times root 2 times root 2, which is, what's that become, guys?
The square root of
2 root 2. Okay, so this is going to be 2/3 times 2 root 2 minus 0. So that's going to be 4/3 root 2. And that's your integral. Now, if you did it on your calculator, you'd have to see what that is as a fraction, and then just compare the two values. Are we okay on how to check this? Yep? Okay. Okay, find the, so now we have this function. Okay, this would be a cubic, and we want to find what's the value between 0 and 2. What's the area under this curve? All right, so just do your integral. 0 to 2, 2x cubed minus 3x plus 2 equals, oh, let's see, we're going to need a little bit more space. So this is going to be, let's see, 0 to 2, 2x cubed minus 3x plus 2 equals, okay, now on this last one, guys, I didn't write out this part. I went right to this part. Okay, but this is really just to help with notation, so we'll do this one this way. Okay, so what's our antiderivative here? Okay, the first part, Eddie, what would be the antiderivative of 2x cubed?
1/2 x to the 4th.
Say it again?
1/2 x to the 4th.
1/2 x to the 4th. Okay, if I did the derivative of that, I'd get 2x cubed. Any questions on how Eddie is getting that? Thanks, Eddie. Are we okay on this part, folks? You're able to do that? Okay. Yes? No? Okay. All right, Anwar, what's the antiderivative of 3x?
Would that be x to the 1/3?
Okay, so if 3x is the derivative, so if 3x is the derivative, what's the exponent on the original, on the antiderivative? No, look, what's this exponent?
0,
1. So what's this exponent have to be?
1,
Pardon me?
3 right up there.
I'm sorry, I just can't. Not 3. It's got to be 1 more than this. This has to be 2. Okay, now, if you did the derivative of that, what's that derivative? Okay, that's 2x, but we want it to be 3x. So what would I have to do to this to turn that into 3x? What are you gonna multiply 2 by to turn it into a 3? Say it again?
1.5, so that'll be a 3/2.
3 over 2, right. Okay, so this would have to get multiplied by 3 over 2, so that would have to get multiplied by 3 over 2. So that's your integral. That's your antiderivative. Okay, Corey, antiderivative of 2. 2x. All right, and now we're going to evaluate that from 0 to 2. So plug your 2 in, do the math. Plug your 0 in, do the math, and subtract the 2. All right, so we'd have 1/2 2 squared minus 3/2, or excuse me, 2 to the 4th minus 3/2 2 squared plus 2 times 2 minus, and now when you plug 0 into all these, you're just going to get 0. Okay, so that's 16 divided by 2, 8. This is 4 times 3 divided by 2, 6, plus 4. So our answer is 6. So the area under that curve would be 6. Pardon me? Good. Okay. All right. Okay, so use the fundamental theorem calculus part 2, which is how you evaluate an an integral, to calculate the following integrals. Okay. All right, so we got F0. Okay, so now you got to figure out what's the antiderivative of negative x squared. Pardon me? So we want to get the antiderivative of this. Okay, so Anwar, what did the original exponent have to be?
The original exponent would have to be 3.
Mm-hmm. Okay, so if I did the derivative of that, it would be 3x squared, but I want it to be negative x squared. I don't want the 3 there. So what would I have to do to this?
Well, would you times it by -1/3?
Yep. So that means the original was times by -1/3. Okay, so we'd have -1/3 x cubed. Okay, and then evaluate that from 0 to 1. And you end up with -1/3. Okay. Now, guys, one of the things you'll notice is this, if we took this with the negative in front of there and we rewrote it like this, do we get the same answer? Will that be the same or will it be different?
It would be the opposite of.
Okay, so let's see. So this is going to be, let's do the antiderivative of x squared.
You need that.
So that would be, the antiderivative of x squared is going to be x, 1/3 x cubed. Okay, and then if you evaluated that, that's going to equal 1, or x cubed minus 1/3 0 cubed. So that's equal to 1/3, and then you're multiplying that integral by -1. So it's the same value. So once I got this part, that's that, then I multiplied it by -1. So it's the same value. Okay, integral of 3x. Okay, Mr. Bess, integral of 3x.
Yes, this, 2 over 2.
3x 2 over 2,
2x, square thing, yeah.
square root thing.
Square root of 3x divided by.
Okay, you're doing the antiderivative.
Yeah, is that it?
So what would the exponent have to be?
It'd be 2.
This would be 2. Okay, now, start taking the derivative of that. What is the derivative of that?
And 2x.
2x, right?
Yeah.
But you want it to be 3x. So if it's 2x, what would I do to this 2x so that it would become 3x? So you're asking yourself, what would you multiply 2 by to turn it into a 3? 3 over 2, right. So this would have to get multiplied by 3 over 2. So that means the original would have to get multiplied by 3 over 2. Now if you did the derivative, you would end up with 3x. Okay, so our derivative of that is going to be 3/2 x squared. So 3x dx, 3/2 x squared, evaluated from -2 to 0. So plug 0 in and then plug 2 in. Or -2. Okay, and this would be, let's see, -3/2 times 4. Okay, and that would be -12 over 2, and that would be -6. Okay, now, this represents an area. How can area be negative?
Below the x-axis.
Very good, right. So if you were sketching this, okay, we would sketch the graph 3x. Okay, so 3x just has a slope of 3 up, 1 right. So it looks something sort of like this. Okay, that's the line y equals 3x. So if our bounds are -2 to 0, then this is the area that you're following. So when you see a negative area, Elijah's exactly right. This just tells you that that portion of the area is beneath the x-axis.
So if you take the integral from like -2 to 2, would the area be 0? Because it's within that area, or?
Oh, that's a good question, below 0. No, the area would be 12.
It would be
Okay,
negative anyway?
the net area would be 0. So it all depends, yeah, so it's a good question. Okay, if we were talking, if we did the interval from -2 to 2, yeah, these two areas would cancel each other out. Okay, but there are situations where you don't want that to happen. And the whole reason that is when we do velocity and when we start doing the antiderivatives with applications, there are times where we don't want the net area, we want the total area. Okay, so the net integral of this, if I asked you, okay, we were doing some sort of physical problem, okay, the total area there is 12. Okay, the net area would be 0.
I thought in the calculator it gave me 0.
Right, because it's giving you the net area. It depends on the context. You'll see when we do applications, when we do the context, it depends on the context of the problem. Right now, if you did this, you'd get 0, which is fine. Okay? The point I was trying to make is you can't have negative area. I don't live in a house that's negative 2,000 square feet. It doesn't make sense. So the point I was trying to make is that this negative just represents an area that is below the x-axis. Okay, all right. Let's see, let's go ahead and do the next one here. So, okay, now we want to get the integral of x squared and minus x. Okay, Eddie, integral of x squared minus x.
The x squared would be x cubed, and then we have or it would be 1/3 x cubed.
Mm-hmm, yeah.
And then the other one would be x squared, or 1/2 minus, or no,
Mhm.
1/2 x, or x squared over 2.
Yeah, same thing, right. Mm-hmm. Okay, and you don't have to do anything to those. If you did the derivatives, you'd get each of those. Okay, so we got x cubed minus x squared over this. And where are we going from 0 to 1? Get your common denominator. Okay.
Would that be negative? The message?
Yep.